Hi there, welcome back to our next section. We're talking about arcs and chords. Remember, have that sheet out so as you go, you can go ahead and fill in the theorems that you're going to use for your lesson checks and your tests. All right, so here's some new definitions for us. We're starting with the central angle, and this is an angle whose vertex is the center of a circle. So this is an example of a central angle. As you can see here, this is the center of the circle. We're going to take two radii and connect it to the side, and this guy here is going to be our central angle. So some more key definitions. We have ourselves our minor arc. The minor arc is part of a circle, and its measure is going to be less than 180 degrees. Okay, it's kind of like when we talk about obtuse, acute, and stuff like that. We're naming things here now. This is all relation to 180. So smaller than 180, we got a minor arc. A major arc is a part of a circle that's going to be between 180 and 360 degrees. When we're equal to 180 degrees, that's when we have ourselves a semicircle. And an arc, it's going to be essentially a diameter. It's going to cut it right in half. Okay, so major arcs and semicircles are named using 3 points, and minor arcs are named using only 2 points. So that's important to note. So whenever I ask find the measure of arc AB, we know we're talking about a minor arc, something that's less than 180. But if I say something like ABC, it's potentially 180 degrees or more. Doesn't have to be. We can name a minor arc using 3 letters, but we don't have to. Okay. So here's an example. We have ourselves a minor arc. We've got 2 of them really in here. So this is minor arc AB. So as you can see, I'm going to be using 2 endpoints of an arc, which would be A and B. And I know that I'm talking about the smaller one that's less than 180 because I'm only using 2 letters. Okay. DA or AD would be the same kind of idea. It's going to be smaller than 180. Example of a major arc would be ABD. So you want to kind of follow the letters. So I start at A, and it tells me to work towards angle B. So I'm going to go towards B, and then finally towards D. So that's going to be bigger than 180 degrees. That's different than naming arc AD. AD would be the minor arc, the one that's less than 180 degrees. So the major arc goes around like here, ABD, and the minor arc would be just listed with 2 letters AD. A semicircle, an example would be BAD, so we would use 3 letters BAD. So typically we wouldn't call this guy here as BD. The purpose of that is because that's kind of telling us, are we talking about the top part or are we talking about the bottom part? Because if we didn't know that, then we wouldn't be able to tell. Like if we didn't know the A in the middle, we wouldn't know that we're referencing this portion of the circle rather than the bottom one there. Okay. All right, to find the measure of a minor arc, you are essentially going to find what the measure of that central angle is. And to find the measure of major arc, you can do that same idea. Or if you're only given a major and a minor, you can find the difference between 360, and that will give you the associate or the measure of that major arc. Okay. There's another way that we can also find the measure of a major arc, and that's using this postulate here. So ding 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 postulate, that means take out that sheet and start writing. The arc addition postulate is essentially telling us that we can find the measure of an arc when we have 2 arcs sitting next to each other, and we can find it by adding them together. Kind of like when we talked about segment addition or angle addition, okay? So we find the measure of arc ABC, so this whole thing here, angle or arc ABC, I can essentially say, okay, well, arc AB is equal to some amount, arc BC is equal to another amount. So if I want to find the whole thing, I can add them together. Again, they have to be next to each other. We can't just take a little piece over here and a little piece over there to find the measure, okay? We got to find the whole thing as long as they're sitting next to each other. We can identify congruent arcs based upon this now. These are 2 arcs that are in the same circle, or they're of congruent circles and they have the same measure. Here's another theorem. Again, there's lots of them in this unit, which is why we're letting you use that cheat sheet. The arcs and chords theorem: in the same circle or in congruent circles, 2 minor arcs are congruent if and only if the corresponding chords are congruent. Okay, so let's take a look at this diagram and kind of analyze what that's saying here. So it's saying in the same circle, or it could be in 2 congruent circles, so just make sure you note that. What we see here, do you see how we have chords AB and we have chord BC? Since these 2 measures indicated by that tick mark are the exact same size, that means these arcs here, arc AB and arc BC, those guys are also the same exact measure. And it's all because these pieces here is the same. And it kind of makes sense, you know, if we're going to cause a triangle here using 2 radii, then and these guys are going to be equal. Think back to like the hinge theorem. these guys have to be the same measure, so these angles here are going to be the same, okay? You can also think of it kind of like these triangles are going to be the same. We got ourselves two radii, so side, 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 which means these angles here, these central angles, they are going to be equal. Therefore, our arcs are going to be equal as well. So um, AB and BC, those arcs are congruent if and only if the AB is congruent to BC. And then the next one is essentially saying that, and also the converse is true. So if I can see that those two arcs are the same, then I know that the two segments or the chords AB and BC, those lengths are going to be the same as well. Okay. All right, next one. We got the perpendicular diameter theorem. So if a diameter of a circle is perpendicular to a chord, then that diameter is bisecting the chord and the arc. So let's take a picture of that, or look at a picture of that. So let's take a look here. I see that I have myself a diameter. Okay, so this diameter here. What has to happen is that it has to be perpendicular. So we have to form a right angle right here. If that happens, okay, we have a diameter and it's perpendicular, then we know that not only is DE congruent to EF, so it's a perpendicular bisector, but it's also talking about those arcs here. So GF and GD, those arcs are going to be congruent. Okay, so this has to be a diameter and it has to be perpendicular. So those are very important things here. The converse is also true. So if I see that it's perpendicular and that either this guy is going to be, these two things here are congruent, or those two arcs measured as congruent, then I'm allowed to conclude that this has to be a diameter, okay? But in either case, either the regular or the converse, we need to have this right angle. If this right angle is missing and it's not told to you that's a perpendicular bisector or perpendicular anyway, we cannot assume that. So that's important to note. So either this is diameter and cuts this in half, or it cuts it in half and therefore it becomes a diameter. So that's how those two guys work there. So make sure you got those written down. Okay, another theorem here. In the same circle or incongruent circle, we've got two chords are congruent if and only if they are equidistant from the center. We kind of talked about this way back when we talked about angles. It was a while ago. Okay, so a couple things have to happen here. So I can say that this length here, CD, is equal to this length here, AB. These two chords are equal only if they're equidistant from this point in the center here. So what is important to note is, do you see how we have right angles here? So this is important. If we don't have these right angles, then we can't say that these guys are the same length. That's the only way to guarantee that we have ourselves some equidistant pieces here. So think back to when we found the distance from a point to a line. We found the perpendicular line to it and then found the distance because that's the shortest distance, okay? So this right angle has to exist, kind of like in that last theorem we just talked about. So these guys are going to be congruent if and only if I can say that EG and EF, those measures are the same. Okay, so if these are the same, then these two are the same. Well, the converse is also true. So if I tell you that AB and CD are congruent, then they're going to have to be equidistant from that center. All right, now that I've overloaded you with information, let's go ahead and start doing some examples. Okay, so let's think about all the stuff that we've learned. So the first thing is talking about the measure of an arc. So what I see in here is that I have arc ML, so this one right here, and that measure is 70 degrees. So again, that represents this piece right here. I can see also I have a diameter LN, as you can see that right here. It's going through the center, so I know that that's going to create a semicircle with LMN. So I can easily find angle P right here by doing 140 minus the 70, okay? Or sorry, 140. Wow, what am I talking about? 180 minus the 70 degrees. Sorry, that is just awful writing right there. So I know that this measure here is 110. So when you're doing these, it's really good to go through and find the measure of each of these arcs before we start finding what the measures are. So what I mean is like fill out the circle with all the individual arcs and then go through and do the problems that you see here on the right. Okay, so what again, I have a diameter here, so that means this main thing over here, that one's going to have to be 180 degrees. Okay, now let's go through and find these measures. Okay, so arc LM. What I see here, arc LM, what I told you before is that it's equal to the central angle of the form. Okay, so it's equal to this angle right here, which means it's going to be exactly 70 degrees. The next thing I want to do is find MNL. Okay, so looking at that, M is right here, and I'm going to follow it. It's going all the way around in this direction, M, N, and L. So there are two ways we can do this. Either we can add 110 and 180 together using the arc addition postulate, or you can do 360 minus the 70 degrees. So whichever one is easiest for you. But this is 290 degrees. Then I'm going to do LMN. So again, I'm indicating this bottom part here, LMN. Well, LN is a diameter, therefore it's a semicircle, so I know it's 180 degrees. Okay, so that's the process that we want to take for these. If you have anything more, you might have to add things, subtract things, and so on. All right, so for this one, we want to find the measure of those red arcs there and determine if they're congruent. Well, I see here that they're both 41 degrees. Okay, so that's the first thing. The measure of arc AC here is 41, and this one here is also 41. Well, they also come from the same circle. Since they come from the same circle, they have to be congruent. How about in this one? Well, in this one, I can see, well, they're both 81 degrees, okay? You can see that this line here, this is 81 degrees, and this one here is also 81 degrees. So while you might think that they are congruent to each other since they measure the same, the issue here is that the circles are not congruent. So you see how this circle is significantly smaller. And the way we kind of think about that is if I were to snip this circle right here, and I were to chop it up right there, and I were to lay these two lines flat and looked at the distance from D to E and A to C, those guys are not going to be the same length. So that's kind of what we're looking at when we're determining if it's congruent or not. All right, here's our last example. We want to find the measure of arc BC. So we're going to kind of look at those theorems that you look down, and we've got quite a few. We got that perpendicular bisector. We got the equidistant stuff. Well, this one talks about the fact that we've got two chords here and here that are the same measure. So since these two chords are equal, what I can say from there is that BD, that arc, has to be the same thing as BC, that other arc there. So what I can do then is take those two expressions and set them equal to each other. So 3x plus 11 equals 2x plus 48, and then it's algebra. Move the x to the left and the number to the right, so the value of x is 37. However, I have not answered my question yet, so I want to find BC. So now I'm going to take that 37 and substitute it back in. So I'm going to do 2 times 37, and I'm going to add 48 to it, and I get 122. So that means both arc BC and BD are both 122. Let's say I wanted to find the mark of the measure of AD here. So what you would do from here, well, I know this one's 122. I know that this one's also 122. So since I know 2 of the 3, I can essentially subtract 122 and 122. So this measure down here is going to be 116. Okay, so note that this whole thing adds up to 360 again if you haven't realized that already. All right, go ahead and hit the stop button, start that practice. Make sure you get any help if you need it. I know we've only did one example from those lots of theorems you talked about, but really you're going to see it's a lot of setting things equal to each other and solving them and plugging them back in and such. Okay, let us know if you have any questions. Thanks.